Welcome to the second video for 3.1 Graphs of Polynomials. Today we will focus on the zeros of our polynomial and their respective multiplicities. So zeros, we should already know that zeros are the x-intercepts. They're where our polynomial's graph hits or crosses the x-axis. Multiplicities will be something new we talk about today, same with sign charts. Those are tools that help us to graph a function, or sketch it rather. And then we've already studied the end behavior, and as we recall from part 1, in order to find the end behavior, we need to know the degree of the polynomial and the sign of the lead coefficient, whether it's positive or negative. So basically we need to know the leading term. And then the y-intercept is something we haven't specifically done in this chapter, but we've done in the past, and recall that to find the y-intercept algebraically, we let x be 0. Once we do all these things, we're able to sketch a graph of our polynomial and then verify that we've sketched this graph using either Desmos or our graphing calculator. Normally, before I get into an example, I like to show the mathematical side of things, kind of not using numbers yet. But in this case, the only thing I'm going to go over between these two examples is the multiplicities. So our first example, we won't understand multiplicity as well, but I feel like if I start with it, you're not going to have any idea what's going on. So instead, I'm going to do a quick example, then delve into what multiplicities are, and then we'll end with a second example. So let's get started with example number 1. Okay, let's take a look at example number 1. We have f of x here is in factored form, which is predominantly, well, it's the only thing we'll see today because that's the easiest way to graph a polynomial is if it's in factored form, because we can easily see what the zeros are. Remember, zeros are what make y 0. They are the x values that make y, or f of x, equal to 0. So if we think about it being in factored form, if either this factor, or if 2 were to equal 0, then we have a 0. Now 2 can never equal 0, because it doesn't have an x in it, it's always 2. But if we think about what value of x makes this factor 0, we can see it's -1. And what factor of x makes this 0? It is 1/2. I'm going to write that out algebraically, just so you can see it. So in order to find the zeros, we set each factor to 0. And then we'll set this one equal to 0. So our zeros are -1. And then this 0 right here will add 1 and divide by 2. So -1 and 1/2 are the two spots where this polynomial either hits or crosses the x-axis. Now, in order to figure out whether we hit or cross the x-axis, that's where something called multiplicity comes into play. Okay, this is going to be my introduction to multiplicity. You don't have to write anything down yet. However, multiplicity, singularly will have a y at the end, this is plural, can be abbreviated mult, M-U-L-T, and the multiplicity is how many times that 0 or that x-intercept occurs. So if we look at x equals -1, it went with this factor right here. This factor occurs 2 times because it's squared. So the 0 of -1 has a multiplicity of 2 because it occurs twice. Then the multiplicity of the 0 1/2 came from this factor, and this factor only occurs once. There's an exponent of 1 here we just don't write, so this 0 of 1/2 has a multiplicity of 1. It's not a super hard concept to figure out the multiplicity, but I will soon share with you what it means in terms of our graph. All right, next we want to find the end behavior. To find the end behavior, we do have to know the degree. So off to the side here, our degree is 3. And our lead coefficient, let's see, this one would just be a 1. 1 squared is just 1. This lead coefficient here is 2, right, just 2 to the first, so 2 times 2. Our lead coefficient ends up being a positive number, which is all we care about, that it's positive. Okay, so that means our end behavior, our right end behavior, as x goes to infinity, what's our function do? What we do is we look at our lead coefficient, it's positive, so our right end behavior is positive. And then our left end behavior, we look at our degree. As x approaches -infinity, what's our function approach? and our left end behavior, our degree is odd, so they're opposite. So our left end behavior will go to negative infinity. All right, now creating, so that was review. So now creating the sign chart. A sign chart is a number line that tells us where our zeros are, and then it finds whether our graph is positive or negative between those zeros. So what I'm going to do is draw out a quick little number line. And on it, I want to make sure that I put my zeros, my x-intercepts. So I need to make sure my sign chart includes -1 and 1/2. Those are the only numbers I need to include on it. So these are x values down here. And up top, it's what f of x equals, or our output. What are our y values? So we know that at -1 and at 1/2, f of x is 0. Because that's where we hit those, that's why they're zeros. That's where we hit the x-axis. Our y value, f of x, is 0 there. That's why they're called that. Now, what I do care about is where is my polynomial? Where's my graph? To the left of 1/2, in between, to the left of -1, in between -1 and 1/2, and over here. I can use both my end behavior and other skills in order to figure that out. So let's try. What we're going to do is pick a number that is to the left of -1, and we're going to plug it into our function. Now, we really don't care what that number is. We care about its sign, whether it's positive or negative. So let's pick a number to the left of -1, since that's this part of the sign chart. Let's pick the number that's very negative. Let's pick -10. Okay, you could pick an infinite amount of numbers that fit in over here. I'm just picking a random one, and I like 10s. So I'm going to pick -10, and I'm going to plug -10 in here. So if we plug -10 in, I'm going to do that over here. We have a 2 out front. Then we plug -10 in for x. And then we plug it in again. So we'll have -21 over here. I kind of ran out of space to write it all in, but I plugged in -10 right here. It just fit. Okay, let's think about the sign of this. 2 is always positive. I care about the sign of each factor. Whatever this is in here, it's getting squared, so that's always positive as well, little plus sign. And then the -21's negative. So if we multiply a positive number times a positive number times a negative number, that means we have a negative output. So I'm going to put negative right here. The next thing we want to do is pick a number in between -1 and positive 1/2. The easiest number to plug in would be 0. 0 is in between these two values. So let's plug in 0. And I'm just going to kind of do this in my head. Whoops, meant to do the pointer. So I'm going to do that in my head and plug in 0. So this stays 2. If you plug a 0 in here, doesn't matter what we plug in, it's always positive. So far we have a positive times a positive, and if we plug a 0 in here, negative. So a positive times a positive times a negative will give us a negative number. Then we want to plug in a number to the right of 1/2. I'm going to plug in, you guessed it, 10, since 10's over here. So let's do that just in our heads. Let's plug 10 in. Positive always. This is always positive because it's squared. And this, if we plug 10 in here, that'd be a positive number here. Positive times positive times positive gives us a positive output here. How do we know that we'll always get the same output whether you pick the number 1, 6, 7 trillion, 10? Those are all numbers that fit here on the number line. Well, I know that because I know my graph is never going to hit the x-axis again. The last time it hits the x-axis is at 1/2. So it's always staying above the x-axis or below it. So whatever number I plug in over here for x, I'm always going to get the same output. Same with here and here. Now, could we have just used our end behavior? We know that at -1, that's the last time our graph hits the x-axis, and it's going towards negative infinity over here to the left. Yeah, it's going down. It's below the x-axis. And our right end behavior says that all the way to the right of our graph, after the last rightmost time it hits the x-axis, it shoots off to positive infinity. So it goes up. So the end behavior actually gave us this value and this value. We really only needed to plug in a number in between here. All right, the last thing we're going to find is the y-intercept. To find our y-intercept, we let x be 0, so I'm going to find f of 0. We'll have 2, and then 0 plus 1, square it, and then 2 times 0 minus 1. And that will equal 2 times 1 squared, which is 1, times, it looks like we'll have negative 1. And then so our output will be negative 2. So our y-intercept is negative 2. Now I'm going to provide or do a rough sketch of f of x. In order to do this, we need all the information that we found. So the first information I'm going to use are the zeros. We know that our graph hits the x-axis at negative 1 and at positive 1/2. And then our end behavior, we know that all the way to the right, our graph goes to positive infinity. So from here, it's going positive. And our left end behavior, our leftmost zero, our graph goes down to negative infinity. I don't know how steep, I don't know if it's arced at all, but that's what I know right now. All right, the next thing I'm going to use is the sign chart and then understanding how that goes with the multiplicities. So it looks like in between when x is negative 1 and x is 1/2, so in between here and here, our polynomial f of x has negative outputs, meaning it exists down here. And that is helped and reinforced by the fact that the y-intercept is negative 2. We have to hit this value here, the y-intercept of negative 2. So our graph it can't go up here. It has to bounce back from this 0 of negative 1 and hit this. Now I don't know if it goes down more and then comes up. I don't know if it goes down here and then comes back up. I'm not sure. But we're providing a rough sketch and this is enough information. So something like that. Again, it might not do exactly that. It might go down and then go back up. I'm not sure. So I'm just going to leave it like that. That's a rough sketch. That's totally fine. All right, let's talk about what that multiplicity means. It looks like at this x-intercept, at this 0 of negative 1, we had a multiplicity of 2. When you have a multiplicity of 2, 4, 6, any even number, your graph does not cross the x-axis, rather it bounces back, kind of like a parabola. That's because the multiplicity there was an even number, 2, at this root, this 0. Then the 0 of 1/2 here had an odd multiplicity, a multiplicity of 1. An odd multiplicity means that your graph crosses the x-axis. It does not bounce back. Let's explore multiplicity in greater detail. All right, pause your screen and get this written down. Here are some of the most common 3 multiplicities, some examples of each. So on each one of these, the 0 is at x equals 2. And when our multiplicity is 1 or 3, odd values of multiplicity, our function crosses the x-axis. I gave 2 examples to show that we could either be going from negative values to positive or positive values to negative, just depending. So if you notice when the multiplicity is 1, our graph just crosses straight through. Sometimes it could just be a linear function or it could be something else, whatever. But at the 0 here, when x was 2, in every example, our graph crosses straight through. When the multiplicity is 3, the next odd number, our graph does go through, but it doesn't go straight through. It kind of looks like a cubic there, and it squiggles a little bit either way. So it does, again, cross the x-axis, but it kind of squiggles. And then when our multiplicity is 2, or any other even number, our function does not cross the x-axis. It still hits it, but it bounces back. Either if it was above the x-axis, it bounces and stays up, or if it was below the x-axis, it bounces and stays down. So these are just a couple examples. They don't always have to look just like this, but this is the general look of the first 3 multiplicities, the most common that you'll see, and understanding the difference between crossing the x-axis when the multiplicity is odd versus bouncing back when the multiplicity is even. In the second example, I'll go through a little bit quicker and won't be explaining every tiny thing. So let's first find the zeros and their corresponding multiplicities. We do have to see that this factor out front does have a 0. What makes negative x squared 0? 0. So when there's an x out front, that means that we have 0 being a 0. So we actually have 3 zeros this time because this factor also has an x in it. So our zeros are x equals 0, and its multiplicity is 2. we have the next factor is x plus 3 and it's cubed, so that means that 0 is x equals negative 3, and that has a multiplicity of 3. And then our final 0 comes from the factor x minus 1, and that means that x equals 1 is the last 0, and it has a multiplicity of 1. All right, the next thing we're going to find is our end behavior. And in order to find the end behavior, we need to know the degree and the lead coefficient. So our degree here is 2 plus 3 plus 1, so our degree is 6, it's even. And our lead coefficient would be this negative 1. We have a 1 here, it's cubed, so it's just 1 times a 1. So our lead coefficient is negative 1, so it is negative. All right, so that means our right end behavior as x approaches positive infinity. Since our leading coefficient's negative, that means our right end behavior is negative infinity. And then our left end behavior is determined by the degree. And since our degree is even, that means both end behaviors are the same. All right, creating our sign chart, we make a simple number line. And we be sure to include all 3 of our zeros. So I'll start with negative 3. Probably need that to be a little bit longer, actually, since we have 3 this time, not just 2. So our first 0 is negative 3, and these are x values. Our second 0 is 0, and our last 0 is at 1. All right, then the values up top will be the f of x values. I'll do those in yellow. And we only care about their sign, or whether or not they make f of x 0. Those 3 values do. Okay, so now we're going to plug in Actually, I'm only going to plug in numbers in here and in here, because here, all the way to the left, our left end behavior says that we go down to negative infinity. So that means that these values all the way to the left are negative, since they go down to negative infinity there. And then all the way to the right, the values to the right of our rightmost 0, they also go down to negative infinity. So I know that I can just fill in negatives here. All right, now I do need to plug in a number in between negative 3 and 0. I'm going to pick negative 1. So I'm going to plug negative 1 into f of x. Okay, so I plugged in negative 1. Note how careful I was here. The negative stays out front no matter what. This is really a negative times whatever we're doing squared. So we first square negative 1 and get 1, but then it's negative. So that out front is really a negative here. Then inside here, we get a 2, and when we cube 2, we get a positive number. Again, I don't care about the number, I care about the sign. And then in the last parentheses, we'll have a negative. So when we do a negative times a positive times a negative, we get a positive output. So values between, our function between negative 3 and 0 is above the x-axis, positive outputs there. Then between 0 and 1, that's a little trickier. I'm going to plug in half. All right, plugging in 1/2. If we square 1/2, we do get 1/4. I'm saying that not because it matters right now, but because you should know that. Anyway, it becomes negative. So this out front here is a negative value. Then 1/2 plus 3 cubed, whatever that, it's positive. Then in our last parentheses, we'll end up with a negative output. All right, again, a negative times a positive times a negative will yield a positive. The last piece of information we want to find before doing a sketch is the y-intercept. So we want to plug in 0 for x. So f of 0 will have us squaring 0, then 0 plus 3 and cubing it, and then 0 minus 1. All right, so it doesn't matter what any of this other junk is here, right? I'm going to end up multiplying it by a 0 out front. So when you do have a 0 out front, it's pretty easy because we'll have 0 times 27 times negative 1. So that ends up being 0. So we actually, we already knew that because since our function hits the x-axis at 0, that means that's the origin. So it definitely, it also hits the y-axis there. Anyway, I just did that because I sort of forgot about that anyway. But whatever, the math made it right and proved that it worked. So we end up hitting the origin. So our y-intercept is 0. So let's do a rough sketch of this with all the information that we have found. Okay, in order to do the rough sketch, I just created a nice, neat XY axes there, labeled them, and made sure the tick marks look halfway decent. That is what I expect of you too when you do these sketches by hand. Again, nothing needs to be perfect. We don't know everything about the graph. We just know these main pieces of information. So let's use the zeros first. So we know that we hit the x-axis at 0, we hit it at -3, and we hit it at 1. The next thing we'll use is our end behavior to guide us. So both our right and left end behavior is negative. That means from the right, our graph goes down, and from the left, our graph also goes down. Then we can use our sign chart and our y-intercept. Now the y-intercept is not as helpful here because we already have the point at the origin, so we're not doing anything different for that. But the sign chart shows us kind of how we move, as well as the multiplicities. So it looks like at -3, our function goes from negative to positive. So it was negative here, and then it needs to cross the x-axis and become positive. The multiplicity at that root, at that 0, is 3. That means we need to cross the x-axis in kind of a squiggle pattern. So I erased what I had drawn because I want to make sure I kind of do that sort of squiggle over there to represent the multiplicity of 3 that 0 has. All right, so we've crossed. Then we have to come back down at some point to hit the origin. And then we don't cross there because we're positive on both sides of that 0, or that root, that solution. And the multiplicity is also 2, it's even, meaning our graph bounces back up. So our graph bounces back there, and then comes back down and crosses when x is 1, and that has a multiplicity of 1. So it kind of goes straight through more or less, whereas at this 0, it's a little bit more squiggly shaped because of the multiplicity there. Okay, so that is a rough sketch of this graph. I'm going to just take a look at Desmos and see how close we are to what the function looks like. All right, this is actually really cool. Check this out, guys. So we can see that our function, oh my goodness, our function crosses the x-axis here at -3. And look, it's totally squiggled there. That's so cool. So that's why it crosses like that there. And then over here, when x is 1, it does pass straight through. Awesome. So we have the general shape exactly right. What we're not going to get right, and it's totally fine, is how high up our graph goes or how, low it does. And we can totally see that our graph shoots up way higher than we thought, and that's fine. We have the general shape of it, we have the intercepts, and we have the end behavior. So that is how you use all those different pieces and basics of your polynomial to create a rough sketch of the polynomial.